Now let me define you the definition of division ring or skew fill. Now a ring R equipped with binary operation plus and dot is called a division ring if it satisfies the following two conditions. That is, if it has a multiplicative identity and every non-zero element has multiplicative inverse. That means it has multiplicative identity 1, and also all non-zero element of R must have a multiplicative inverse in R itself. Now example of division ring is this one. If you consider M is equal to set of 2 cross 2 matrices A, B, B bar, A bar, such that A, B belong to R complex number and A bar, B bar are conjugates, then this one form a division ring. It has multiplicative identity, this one 1 0 0 1, because the conjugate of 1 is 1 itself, and then the conjugate of 0 is 0 itself. So therefore this one acts as the multiplicative identity, and every non-zero element also has multiplicative inverse. You can use this row operation or the determinant rule in order to find out the inverse of each element of this one, and that inverse also still belong to M. So now here it is not a commutative ring, this one, because if you take A to be this one, 2 plus I minus I and then 2 minus I, here you see that what is the A is equal to this one, B is this one, conjugate of this one, that is A bar, here it is 2 minus I. If you take B is minus I, the conjugate of minus I will be I, and then B is equal to this one, 1 plus I, then 1 minus I, and then this one is I here, and the conjugate of I is minus I. So if you take AB, then this one will give you this matrices I minus 2, 3I, and here it is minus 3I, here it will be minus I minus 2. And BA is equal to this one. It will be equal to 3I minus 2, then 4 plus I, and then here it is 4 minus I, and then minus 3I minus 2. Now if you check, if you see this one, AB is equal to this one and BA is equal to this one. So this implies that AB is not equal to BA. Therefore it is not commutative. So this is a division ring because it has multiplicative identity 1 0 0 1, and also every non-zero element of M every non-zero element of M has an inverse in M itself. So it is a division ring, but it is not a fill. Note this one, every fill will be a division ring. That means if F is a fill or R is a fill equipped with binary operation plus and dot, then in that case it will be a skew fill. Why? Because by definition of fill must satisfy the axioms. Number 1, it has multiplicative identity. Number 2, every non-zero element has multiplicative inverse. And one more condition is that it is commutative. So that third condition, commutativity, is missing from skew fill. So every fill will be a division ring, but the converse is not true. Every division ring is not a fill. So the simple example is this one only, because it is a division ring. It satisfies the first two properties, but it is not commutative. You can see from this particular value of A and B, AB is not the same as BA. So therefore every division ring is not a fill. Now let me come to the next definition of a subring. Let R and the plus and dot be a ring and take S to be a subset of R. Now if this binary operation plus and dot induces this binary operation in S in such a way that this S also under the same binary operation plus and dot satisfy all the ring axioms, then in that case we call S and the plus and dot a subring of R and the plus and dot. Now here the simple example is this one. The ring of integers under the usual addition and multiplication is a subring of ring of real numbers under the same operation, addition and multiplication, because we know that set of integers is a subset of R, and the same binary operation in R, the binary operation plus and dot induces the binary operation in set also in such a way that this also satisfies the ring axioms. But now if I take the ring of integers 0 plus or minus 1 plus or minus 2 and so on, Under the binary operation plus and dot, that is set under plus and dot, this one we know that it is a ring. But if I take a subset of S as 0, 1, minus 2, then 3, 4, then say minus 6 and minus 6. This one, even though S is a subset of set, but it is not a subring of set. Why? Because you can see from here that what is 1 plus with minus 2, this is equal to minus 1. But minus 1 does not belong to S. Similarly, multiplication. Minus 2 into 1 into, or I can take this one, 3 into 4. 3 into 4 is equal to 12, but this 12 is not an element of S. So therefore, this set, even this S, even though it is a subset of a set of integers, but it is not a subring. To be a subring, the binary operation plus and dot in that ring must induce the binary operation in that subset also, in order that that subset also become the ring or satisfy all the ring axioms. So I hope with this one it is clear now. Now let me come to this one theorem. The necessary and sufficient condition for a non-empty subset S of a ring R to be a subring is that A belong to S, B belong to S. It will always imply that A minus B belong to S and AB belong to S. So now here the proof is the if part. Suppose R and the plus and dot, this one is a ring. Now if it is a ring, or let this one be a ring, and S and the plus and dot be a subring, of R. Now if it is a subring, then in that case S and the plus this one is an abelian group. That is by the definition of a ring. So first of all, S and the plus should be an abelian group. Now if it is an abelian group, so what I need to prove is that for A it belong to S, B belong to S, A minus B belong to S, and AB also belong to S. So AB belong to S will imply that A minus B is equal to A plus of minus B. This also belong to S because S is a group. So this implies that A minus B also belong to S. So the first condition is satisfied. Now for any A belong to S, A belong to S, B belong to S. Since S and the plus and dot satisfy all the ring axioms, so that means multiplication also induces the multiplication in R also induces a binary operation multiplication in S also. So for any A belong to S, B belong to S, it implies that A, B also belong to S. So therefore the first part is done. That is, if S and the plus and dot is a subring, then we will always have this condition. Now conversely, suppose for any AB belong to S, A minus B belong to S, and AB belong to S. So what we need to prove is that S and the plus and dot is a subring. So how to prove that this one is a subring? By using this condition here. Now since A and B belong to S, it implies that A plus or A minus B is equal to A plus minus B also belong to S. Why? Because S and the plus, this one is a subgroup of R and the plus. So therefore, and also R and the plus, okay, here this one, A belong to S, B belong to S, it implies that A minus B belong to S. Why? Because with this assumption here, we are able to show that for any A, B belong to S, A minus B is called A plus of minus B belong to S. Now S plus, this implies that S and the plus is a subgroup of R and the plus. Now here, for any A, B belong to S, A, B also belong to S. So this implies that multiplication in R also induces the multiplication in S, because the product of two elements in S still belong to S. And also since this one, R and the plus and dot satisfy the associative law under multiplication, and since S is a subset of R, so associative law also satisfy in S. And similarly, since the distributive law in distributive laws in R and the plus and dot holds, therefore in a subset of R also it will be true. So that's why with the assumption that AB belong to S, A minus B belong to S, and AB belong to S, we are able to conclude that S and the plus and dot is a subring of R. Now let me define the definition of this one. Left ideal. Left ideal of a ring. A subring S of a ring R is said to be a left ideal of R if for all R belong to R, S belong to S, the product R into S. That means if you multiply the element of R from the left side of an element of S, then in that case, that ideal is called as left ideal. Similarly, if you multiply S from R from the right side of an element of S, then in that case it will be called as the right ideal. If S is a left ideal and a right ideal at the same time, then in that case it will be called as a two-sided ideal of R. Note that, for example, this one, 2 set under plus under this one is a left or is an ideal of set under plus and dot. Because what are the elements of 2 set? 2 set contain the elements 0, plus or minus 2, plus or minus 4, and multiple of 2. Now if we take for any M belong to 2 set, then M will be of the form say 2A, where A is an integer, and for every R belong to set, then R into M will be equal to R into 2A, which is equal to 2ARM. Similarly, M into R is equal to, it will give you 2ARM. So this still belong to 2 set. That means there are multiple of 2, so it will belong to 2 set. So therefore, this is a simple example of an ideal which is both left and right ideal. Now, not every subring will be a right ideal. You can see from this one, for example, if we know that cube and the plus and dot, this one is a subring of set of real number and a plus and dot. But this one is not an ideal. For example, if I take a rational number 2 belong to R and then say 3. 3 is a rational number. Now what is root 2 into 3? It is 3 root 2, and this is no more a rational number, it is just a real number only. So it belongs to R but does not belong to Q. So therefore, Q is not an ideal of a set of real numbers under the usual addition and multiplication. Now here also we have the same thing, just like in a subring. The necessary and sufficient condition for S to be a left or a right ideal of R is that for any A minus B, AB belong to S, A minus B belong to S, and the second condition is that R belong to R and A belong to S, RA must belong to S. So here the first condition is trivial only, because if I assume that S is an ideal of R, then for then S and the plus will be an abelian group. So which means that S is an abelian group. So A, B belong to S will imply that A minus B is equal to A plus of minus B. This will belong to S. And since it is an ideal, so for any R belong to R, RA also belong to S for A belong to S. But the converse is also true. That means if AB belong to S, then also A minus B belong to S and RA belong to S, then this will implies that it is an left ideal or a right ideal. This follows from the proof of that one, the necessary and sufficient condition for set S to be a subring of R. So with the assumption that A minus B belong to S, you'll be able to conclude that S and the plus is an abelian group, and also with another assumption that is A and B for A belongs to S, R belong to R, then RA also belong to S. So this will implies that it satisfies the condition of the definition of ideal, the left ideal. So therefore, the two condition A minus B belong to S will implies the A minus B belong to S, and then also AB belong to S implies that AB belong to S. This together will implies the S and the plus and that is a subring. And the condition that R belong to R, A belong to S will implies that RA also belong to S will implies that it satisfies the definition of a left ideal. So together with that definition, together with this condition, then we can conclude that S and the plus or this one, S is a left ideal of